Hello and welcome to our first lecture. Today I want to show you how you can go from modeling into simulation, basically motion simulation or R simulation type. So I first start with the modeling. I need to add an assembly. I want to model a basic mechanism, a pendulum now. So I add the master assembly. On the top right corner you can see my clicks and keystrokes if you want to. I have some customized short keys, but most of them are similar to the NX defaults. So now I have the pendulum assembly and I can go to assemblies and start adding new components. Don't worry about the names. We can change the name when we save the file. So I added a new file. This is going to be the main pin that I want to uh, connect the pendulum to it. Double click on the pin or the new part to make it as a work part, and now I can start sketching. The dimensions are not important for now. Any dimension is okay for now. Just gonna make some numbers and I'm gonna extrude this circle to make a pin. So we have the pin. I can now save, and here I can name it as pin. To add another part or component, double click on the master assembly and go to the assemblies and new component. Click OK. You now have another part. To start making that part, double click on it to make it as a work part, and then you can start sketching. This part, the location of it has nothing to do with the other part. In fact, we can move it around later or using assembly constraint to fix them together. But I'm gonna draw it on the center as well, so we have no problem. I'm gonna make some clearance between these two parts, and maybe this big. Then I want to have an arm of like 70 is okay. Maybe I add another circle here too. And also, yeah, I can come back here and show you how you can actually modify the parts that are connected to the simulation. So I think this is good for now. I'll finish this sketch. I will extrude this part, let's say 10 millimeters, and click OK. So now we have two parts. There is no connection, but you can go to assemblies and assembly constraint to actually connect. For example, let me just center these two parts. You can basically go to the assembly constraint. Here, center 2 to 2 means you select two faces, this face and this face. Should be centered in this face and this face, like this. So all these assembly constraints will help you to move the objects to construct your initial condition when you move to the motion. So let's move to the motion. I think it's enough for now. Let me save. I will call the next part the art. This part wasn't named, so that's why NX is asking for a new name. And you can come back here and edit all the parts whenever you like. Let me just hide the sketches and assembly constraint so we have a better view. And also we can change the colors so we have a better view. Let's change the color of this one. Just so it's easier to distinguish. And now I can go to application and click on motion. This will open the motion application, all things are grayed out because you need to first make a new simulation. And as you can see, you can add multiple new simulations basically. So you have a model, like a model of pendulum, you can simulate it with different scenarios. So that's why you can keep adding new simulations. The naming is okay for now. I add a new simulation. Here it will ask you if you have a component-based simulation or not. Basically, it should be always checked. This means that you have a geometry section in the Motion app as well. Well, where you can make some basic shapes and geometries. So you don't even need the modeling app. But here, if you check this, it means that you want to bring the assembly that you already had from NX modeling to the Motion, which is actually recommended, and these geometries and the option is basically useless. So keep it checked so you can use the stuff that you made in the modeling app. The next option is a start joint result. This will read the assembly constraints and try to guess if it's kind of a mechanism that works with joint. For example, if you have a revolute constraint, not a joint constraint here, NX Motion tries to guess that you probably have a joint here, and it will set up a joint for you. I usually recommend to do everything from the beginning and don't rely on the constraints you made on assembly unless you made a very clean assembly where all the constraints are in place. Otherwise, add the joints and other links again. It would be more helpful. So I click OK without checking that because I didn't define any constraint actually. So you can see here that now we have our new simulation. Here in the description, you see it says SimCenter 3D Motion. This is the solver that the software will use. And these lectures that I'm giving, we are not using this type of solver for multiple reasons. I will switch to Recordine. Main reason is that Recordine is using signal charts and DC motors, which are very useful. Also, it is possible to co-simulate with MATLAB. The main solver is the SimCenter 3D Motion. NX is still working on it, and it's a good motion actually, good motion simulations or good solver. But Recordine is more useful, at least in our application. I will explain more about this later. So here you can switch the solver. Also, you have access to a lot of other stuff that are also appearing on the top. So if you couldn't find something, you can right click on the motion, or also you can use the menu and use insert to add other stuff, which I will use later. So we have the simulation. The first step is to make motion bodies. Motion bodies are actually objects. Anything could be a motion body. This used to called link in the old version because uh, a mechanism is nothing but some links and joints. They changed the name to motion body. Enix is changing names a lot, so you better get used to it. Now it is motion body, which means an object. For example, this part is a motion body. This part is a motion body. And it is different than a part because, for example, you can put two or more parts into one motion body and they just act as a rigid body. So instead of connecting stuff inside your modeling app, you can just bring in your assembly, but then make everything as a rigid by adding them to one motion body. I can show you that later when we have a more complicated setup. Before the motion body, we have two options here. It's a solution and under it, environment. The solution is necessary. It adds a solution to your simulation, and as you can guess, you can add multiple solutions to one simulation. For example, you can have multiple scenarios inside a solution with different parameters. For example, you can have multiple directions for gravity, or zero gravity, or gravity on, or different timings, or different options. Let's take a look at the options. The solution type here, you have a normal run, articulation, spreadsheet run, and flexible body. Normal run is what we are going to use for now. And the other important one is flexible body, where you can actually see the stresses on different parts. You can actually run a finite element simulation and see the deformation of the part. Remember that in motion simulation, all links or all motion bodies are rigid. But if you select flexible body, this will give you the option to change some of the parts, some of the motion bodies to flexible parts. So as your device is moving, you can actually read the stress and strains or deformations on the part. So remember these two, normal run and flexible body, are very important. Articulation is a kind of real-time solver, so you can grab something and move it around and you will see the real-time effect, but it's not possible on all the scenarios. For example, you can't have contact. You can't have some of the options. A spreadsheet run is saving all steps into a spreadsheet, as the name says. I will go with the normal run, and then analysis type, you have three important options. You have kinematics, dynamics, statics, and control dynamics, which I'm going to use now, but it's grayed out. I will show you why. The kinematics dynamics will define that you need movement and forces inside your simulation. While the statics, as the name implies, nothing moves, you can just read the forces. There is no motion. On control dynamics, you can have a couple of motors, like DC motors, connected to your simulation. So why is that grayed out? I have to go back to the environment. Now you see that here I can choose if I want kinematics or dynamics, and then I have motor driver, which I need. That will turn on this DC motor for me. For now, I don't need code simulation, but later on I'm going to use it. This means that I can use MATLAB Simulink to control my motors or read the sensors. Also, if you want to read some deformations, you want to see some deformations and read the stresses, you should turn on the flexible body, which is a bit complicated for now, but I can show it later. The kinematics and dynamics are different in a way that in kinematics, no force or torque is involved. It's only movement, it's only motion without any force being applied. So if you select kinematics, you can just move stuff around without being able to see any result of forces being applied to different parts. While in dynamics, you have all the options available, including kinematics. So if I click OK, now these two options that I need are turned on, and if I go to the solution, I can put it on control dynamics. Time obviously is the time span of the simulation. The steps shows how many steps you want to have. Think of it as resolution of the simulation. And then you have the gravity, which is important now. If you look at my setup, the software is automatically taking z-axis as gravity, which I'm going to change the direction. So you can click here, and then you will see the direction of gravity has changed to what we want. And the rest of the options are options for the solver. The default settings are good for almost any simulation. So you don't need to change these things unless you have some specific simulation or your simulation is failing. For example, the initial step size or error tolerance depends on how much accuracy you need or how fast is your computer, for example. But the default settings are good. So I click OK and it will add a new solution, solution 1, to my simulation. As you can see, I can go to solution and make another one, maybe with gravity on another direction or longer time or shorter time just for a test. I click OK, and if you have two solutions, you can always activate one of them. If you right click, you can go to deactivate. I don't have two here, so it doesn't show up. But first, let's start with motion body. First thing, it will ask for an object. So I select the first object is the arm. I name it arm, and I will leave it as automatic. So it will fill up the mass and other properties of this object. I click apply and I can select the pin as the next one, same settings, and it will calculate the mass. Let me show you. If I go back to the arm, now we can see some information. For example, this arm is 2 kilograms. Now, how does that know? If you go back to the tools and assign material, here we can select objects and assign materials that we want. We could also do it inside assembly. Let me, for example, here use aluminum. You could do this inside the modeling app. Let me save here. Or we can define it here, no difference. You can always go back and change things if you want. And now you see it's around 1 kilogram. I think the default was on a steel, so it's now lighter. So this is how it's calculating the mass, moment of inertia around different axes and other stuff. Also, the center of mass is being calculated automatically based on the shape of your object. So now we have all motion bodies here. To connect motion bodies, you need to use joints. This is the joint dialog box, and I'm going to explain different parts of this dialog box. Here you can select different types. This is very similar to assembly constraint. It gives you a lot of options. I will cover most common one of them. But first, we need to fix the pin. So I use the fixed joint and select the pin as the motion body. The origin is not important here. It's basically the place that you fix and the direction of a fixed point. You can use fixed joint to fix something to a space, as I did, or you can fix one object to a base. So if I select another thing like a wall as a base, it will fix a pin to the wall. But if I don't use the base, it will be fixed in a space. I click apply, and here is our first joint, and you can see it under the joints on the motion navigator. Other types that I'm going to explain are revolute, a slider, and cylindrical. I will go back later and explain the rest of the joints. But to explain these options, I made these joints here in a separate file so we can talk about them. First one is the slider. Very simple type. You can use this for having two sliding body as the name implies, and this is the type of movement you have. Now this will generate a different reaction force. For example, if you have movement along these directions, or this direction, or this direction, this will generate a kind of reaction force inside the joint. So the joint won't allow any kind of movement except this type. Any kind of movement other than this, it will generate reaction force inside the joint, and it will affect the friction force inside the joint. So this is a slider, and I will come back to explain the friction on this type of joint later. Then we have the cylindrical joint. Here, this is a cylindrical joint, and it's very similar to the slider joint, but it can take the rotation along the axis of the joint. So the movement can be like this, and it can also rotate. Here the shaft is uniform, so you don't see the rotation very good, but it can rotate without any problem, as you would expect. And it can also slide. So there won't be any reaction force generated when we rotate it axially. And the last one that I want to talk today is the revolute joint, which I'm going to use on the pendulum. The revolute joint is very similar to the cylindrical joint, but it won't allow the axial movement. So it can't move like this. As you can see, there is a little bit of gap here in between, but the caps or the ends and the sleeves won't allow any movement, as the contact will stop them from movement. So the only movement is the rotation along the axis of the shaft. That's the only movement that is allowed in the revolute joint. So let's go back and make a revolute joint between the pin and the arm. Here I go to the joint again. I select revolute, and you see more options are now opening up on the top. These options depend on the type of the joint you select. The fixed, we don't have any other options, but under revolute we have friction and driver. Let me first make the joint, and then I will explain the friction tab. First, you need to select action and a base because you want to revolute two bodies together. Again, like fixed joint, you can revolute an object or a motion body into a space without connecting it to any other object. But here I want to connect the arm to the pin. Now, which one is the action and which one is the base? Mathematically, there is no difference, but it is recommended to select action as the body that moves more. So here the arm moves more and the pin is stationary. So I select pin as a base and the arm as the action. So I select the arm. Unlike the fixed one, the origin and vector is important here because that's how the software calculates the reactions. It will look for the origin and the vector. The origin is in the center of the arm, so I go with between 2 points. I want to pick a point between these two arcs, and with a vector perpendicular to this, or I can just go with the perpendicular, or we can go with the curve or axis vector and select this one. And this is the vector we're going to use for the revolute. This is the direction of the axis, and then we use the pin as the base, and we have our revolute. I'm gonna make it a little bit bigger. Just this is just the display scale, and it's not affecting the motion. And click OK. So we have a revolute kind of joint. Now if we go back to the joint that we made, joint number 2, you will see that we have two more tabs, friction and driver. So when you define a joint like a revolute joint, to make it realistic, you can add friction to that joint. And also you can drive that joint without adding any motor. But I'm going to explain this later because we don't need to drive this joint for now. So let's go back to friction. And let's check different parameters. Now to understand these parameters, I need to go back and explain the friction, the physics of friction. So here you see the model that the software is using. It is defined as the friction is defined as the coefficient of friction, or mu, multiplied by the normal force. This normal force is very important, and as you can see here, if I go back to the joint, there are different normal forces depending on the type of the joint. But let's see a very simple type of friction, which is a simple object, flat object on a surface, which we are pulling it with another mass and a cable. And also we have the weight of that object applied to it as the normal force. So obviously there is friction between these surfaces, and there is a force that you need to apply before it starts to move. This type of linear definition or linear function, linear relationship between the force, normal force and friction force is called Coulomb model, because Coulomb first came up with it. So it's very simple. It's just the normal force and some coefficient, some constant that you multiply to the normal force. So as you can see, the area of the contact has nothing to do with the friction, and this is very important. Here, Da Vinci first tried to do some tests to verify this Coulomb friction and find out if the area is also effective into the friction force. So he made this setup with the exact same type of brick, but with different orientations. He applied force until it starts to move. So after doing the test and applying the force, it's the same amount of force that he's applying to the object. He found out that all of them will start to move with the same amount of force, no matter what area is in contact. So you might think that this one, let me highlight this. So for example, you might think that this object will resist more because the contact area is bigger, but apparently, as you can see in this formula defined by Coulomb, there is no area here. So the area has no effect on the traction or friction force. And why is that? It's pretty simple. Here, these two are same because in the first one, you have actually bigger contact. That means that more atoms are actually interacting with each other, but there are less atoms on top of them. So there is less force on top of each atom here, even though you have more atoms, uh, but there is less weight or less, let's say, pressure on top of each one. While in this one, the B, you have more atoms on top of the one on the end, but then you have less atoms in the area. So less atoms are interacting. So this actually makes all of them equal and no difference between the traction force. Now, this friction coefficient, mu, is not actually constant. It is constant, but depends on the velocity and some other parameters. But you can assume it as a constant in some simple conditions. So let's take a look at the friction coefficient and how the software is actually calculating that. Because if I go back here into the friction tab, let me open the joints we have here. Under friction tab, you have all these parameters, especially mu static and mu dynamic. So it seems that we don't have just one number for mu or friction coefficient, and it is changing. And the software is considering that change. And this is how it is doing it. So basically, based on the theory, there are two types of uh, friction. namely static and dynamic. It's the behavior is pretty simple. In a static, you have the object. This is a larger scale or magnified uh, contact surface. So on the magnified contact surface, whether you have a rough or even a smooth surface, you have all these peaks and bumps that interlock together. As you start to apply force, these interlocks start to open and slide on top of each other. That's where the friction starts to go up. And we see that in the friction coefficient. So it will go up, and at some point, these peaks can be skipped by the red part. So it actually jumps next and skips to the next peak, as you can see in the dynamic. So this is where the object actually starts to move. We have very little movement in the static friction, which we call them creep or micro sliding. And this is under some, let's say, velocity delta V, which we call it threshold velocity or a stiction velocity. Until this point, or until a stiction velocity, we can consider the objects static. So the friction coefficient will be the mu static, which is always higher than mu dynamic, because as the object starts to slide, the friction coefficient drops, because as you can see here on the right side, the object starts to actually uh, skip all these peaks and bumps. And it's easier for the object to move. And some of these peaks actually break and make it even easier for the object to slide. So that's why the friction coefficient drops down. Now, this is a very complicated curve, but the software needs to calculate that, and therefore it has this kind of algorithm built into the motion application. So it starts with mu multiplied by creep coefficient. This would be mu s. So we are still in the static region, but even inside the static region, if you look here, so we are still in this region, and in this region, you have to start from 0 up to mu s. 0 is where there is no deformation or there is no creep. So it means there is no force being applied. As the force goes up, this coefficient C or deformation or creep goes up. As a result, the friction coefficient goes up. Until mu s, this is where we reach delta V or stiction velocity. It hits the maximum friction coefficient, which is mu s. After that, the software has a limit on between the delta V and 1.5 delta V. It will interpolate this area with a smooth function like this. Now it doesn't matter how it will calculate it, but it will interpolate between this number at this point in the top and mu dynamic at this point. So anything is in between is being interpolated until it reaches 1.5 V and then sets dynamic mu as the friction uh, coefficient at this point. So between a static and dynamic, it uses this function to interpolate. Now let's go back to the option and see what we have here. Let me start with the explanation on this slide for each one. First, we have a slider joint. Let me go to the slider. And this is the block algorithm that shows how the software is calculating the friction torque. So as I enable friction, it will start to calculate this red friction force. So this is the output. The inputs are the reaction forces and torques, which you see as F. This is some arbitrary force that is being applied to the joint. And we also have two torques being applied to the joint in a very general condition. And the joint is also, this pin is sliding inside the joint. So these are the given or inputs. Here you see, first it wants to calculate all the normal forces, because what you have here, as you can see, is the normal force and the friction. You need to calculate these two. First, the normal force. There are different normal forces that you can calculate here. First one is coming from this torque that is being applied to the joint. Now this torque generates a friction inside the joint depending on the overlap of the joint. Let me show it here. So there are different conditions that you may have on a slider. You may have a slider that moves like this. There is always 100% overlap inside the joint. But you may have some condition like this. Now, if I apply torque like that, the force being generated inside the joint is different than this condition, for example, because the arm of the overlap is different. Another option that you basically have three options. Either you have a constant overlap like this, the overlap remains same. You can have a decreasing overlap, meaning the pin is moving out of the joint, so the overlap is decreasing, or increasing overlap, meaning the pin is being inserted to the joint. So you have all these options. If I go back here and open options for friction under slider joint. Here you see you have the overlap as constant, increase or decrease. So here the software finds the overlap by using that constant alpha and the displacement, initial displacement of the joint. When it finds the overlap, then it divides the moment by this overlap to calculate the force. If you look here, let me use this draw. So the first normal force that we are trying to find to use it for calculating friction looks like this at some distance, which is shown with xs. This xs is being calculated as the overlap plus the displacement of the joint. So if I have this Tm, I can just divide it by the arm, and that will give me some kind of F or normal force inside the joint. So we can actually replace this torque by this force, which is the torque divided by xx, as you can see here. As you can see, this goes inside this summation, and then the magnitude comes out and goes into another summation to calculate the friction. So what is the next? The next is the direct force that is being applied to the joint. So we had a torque that was being applied to the joint. We calculated the force here. Now we have a direct force that is being applied to the joint. If there is any, we are considering a general condition. For this force, we don't need to divide it by anything because it's a force. We just need to find the normal force, normal component of this force. So we will find the normal component with this magnitude, and it goes inside the summation. Then we have another torque, which is the axial torque being applied axially. It is, let me show how it looks. Now we are considering the axial torque that moves the pin like this. This will also generate friction because it is generating a normal force. So the software is estimating that by dividing it, anytime you want to go from torque to force, you have to divide it by some kind of arm because that's the definition of a torque. Torque is basically equal to some kind of arm multiplied by a force. So of course, you can find the force by dividing the torque by this arm, right? So here we have another torque, which is axial. The software needs a kind of arm to find the normal force. It is using Rn or reaction arm. It is estimating, as you can see, this is kind of estimate of a pin that would be similar to the size of this square. So if I go back to the option, this reaction arm or Rn, we specify that here. If I go to a slider joint under friction, you have the reaction arm here. So this is where you input that. Also, this is initial overlap. The software will divide the torque that is being applied, Tm. So this is basically XS, initial XS or XS0. You input it here, initial overlap. And then you select overlap delta constant. So this will calculate the force that is being generated because of a torque on the joint. So let's move on. We calculate Tn based on this arm leg, reaction arm here. Remember, the software cannot read the geometry, so you have to input all these numbers. Even though you have the size of the pin and size of the arm, the software cannot see that when you define a joint. So it's totally separated from the geometry. There is no automatic system that reads your geometry. That's why you have to input all these numbers. Otherwise, the pin looks good, the arm and hole looks good, but your joint is acting totally different. So make sure the numbers you put in here matches the numbers you have on the pin. For example, my pin here, I think was 10 millimeters. So the reaction arm, which is the radius, it should be 5. So make sure that your numbers matches the model. Otherwise, you get wrong numbers. Now let's move to the next. The next one, let me see how I can use the eraser. I'll erase all of them. Now the next one, the next force that it's calculating is this, not calculating, but reading, is this preload. You have to input some kind of preload. Now what is this? The preload, you have it here. You can select or deselect it here actually, and then you should input your preload here. This preload is the minimum force you need to apply before things start to move. Now, most of the time it's 0. That means your system will start to move with any load. But in reality, you have some kind of clearance or tolerance between all these parts. So, for example, in this slider, it's not perfectly in the center, or it's not perfectly sized, or you may have some kind of interference between these two. So when you want to move it, you need to apply a lot of force before it starts to move. That is called the preload. In a slider, you only have preload force. There is no preload torque. But for example, in cylindrical, it may stick to the outer joint and you may need some preload to be able to start the movement or start the rotation. So it will be calculated directly from the force, and it will divide it by friction, because here, if I go back again, you input the friction force, not the normal force. It's set like that because in experiment, you can calculate the friction force directly. You put some force, you put a load cell on your mechanism, and you start to apply force until it moves. That will give you the direct friction. Let me put it on a slider. You will get the direct friction preload force. So the software has to first divide it by the static friction to find the normal force. Then it will add it with other normal forces from other places that we talked about, calculates the final normal friction as this, and then here you have the final normal force acting on your system. So going back here, you have Fn now. The next step for the software is to find friction coefficient here, which is coming from FRD. This FRD is this friction regime determination, or this one. It goes inside this to read the friction coefficient now. At each time step, it is doing this, because at each time step, the creep, velocity, forces, and everything may change. So at each time step, it finds the normal force, then it goes back here, calculates the friction inside this green box, and then gets the friction coefficient. It multiplies, as it's shown here, that with the friction coefficient to find the final friction. So these are the parameters that I have for the joint. Let's take a look again. I enable the friction. The static, as I said, should always be bigger than dynamic. Be careful with this. It may return some lockup error. That means your friction, the static friction, is too much that nothing can start to move. So you have to be careful with the difference between these two. So at what point you want the software to go from static to dynamic? If I go back here, this means delta V, or this line that I have here. Let me show it with red. This line here, or delta V. At what delta V you want the software to switch to dynamic, you write it here. And these information you can find on the data sheet of the component that you are modeling. And then this is creep, the maximum stiction deformation. This means at what point the software should start calculating friction. So this is down here. You tell the software, or it's actually the minimum number for C. At what point the software should start calculating the friction, and you write it as a deformation. So this is 100th of a millimeter. This tells the software if you have 100th of a millimeter deformation between these two, you should start calculating the friction. You can completely disable one of these two effects, one of these two sides, left side or right side here, named stiction or sliding. So if you think if your simulation starts with a motion, or if there is no motion at all, you can just select it. This will make it a little bit faster, so the software won't look on the other side of the graph. Here you can check or uncheck these forces. Each one of these forces, let me clean out a little bit. This is yes. So each one of these, sorry, this force, this one, and this one. Actually, there is three. The other one is calculating. So preload, reaction force, and bending moment. It's these three. You can check or uncheck any of them. So the software is not going to that loop to calculate the normal force based on that. So for example, if your joint is free to move from the beginning without any sort of resistance, you just turn off the preload and you don't need to fill this up. Same with reaction force. If you don't want the software to use the reaction forces to calculate friction, you can turn that off, or even bending moment. You can turn everything off. There is another option at the end, which is enable the max friction torque. This means you can limit the amount of friction that is being transferred between these two parts. So this is going to cut off torque. After that, the software won't calculate friction, so there is no friction force. It's like it's free to move after this amount of torque. It's like having a clutch. At some point, it applies the clutch, so there is no torque being transferred. So these are the options you have for a revolute. For a slider, the options are very similar, and cylindrical as well, very similar options. And you can see here the one option you have is limiting maximum force, because not only you have torque being applied on a cylindrical part here, you also can limit this kind of force. So after some force, it will move without any resistance. So let's move to the cylindrical joint. The only difference that you see between a cylindrical joint and a slider is that it is free to rotate. So you have this rotational velocity, and also you don't have this Tn here, which is the reaction force that being resisted by the joint. But on a cylindrical joint, there is no resistance for the rotation along the z-axis. So it is free to rotate. There is no torque, no reaction torque. Therefore, there is no friction based on that reaction torque. Last but not least is the revolute joint. There is a difference. It is very similar to a cylindrical joint. The only difference is that there is no axial movement, because there are two end caps resisting the movement. And because we have end caps, there are friction between the end caps and the outer side of the joint, here shown in gray. So between the red part and the gray part, we're going to have friction if the axial force increases. So that's why we have this FA, which is the axial force in the axial direction like this. And we use different friction arm here than what we had in the slider joint, which we pick as the average radius between the pin and the outer side of the cap. So in our joint here is highlighted at this circle. So this circle radius will be our Rn. And the software uses that Rn and multiplies that by Fa to find the reaction force, or the normal force, that is being used to calculate the friction torque. Remember that in a slider you have friction force because you have a sliding action, but in a revolute joint you have friction torque because you have torque or rotation action. So you're going to have a rotational resistance, and as a result you have a torque kind of friction. While in cylindrical you have both. You have the movement along the axis, which generates the axial friction force, and you also have rotation, which will generate the torsional torque, torsional friction. Now let's move on to the simulation. Here in the navigator, you can easily move around and see what is connected to what. For example, if I click on the first joint, it will highlight the arm and pin. This is not a complicated or big assembly, so it's easy to find everything. But if you have a big assembly, then this clicking on joints is very helpful. For example, the second joint shows me that only the pin is involved. And can use this to find out what is connected to what. Now I can save here, and here you see that I don't have any initial condition. So let's run it and see what's happening first. The simulation is finished. I can play it. There is a little bit of shake here. See that it's moving a little bit. I think we have a problem also here. So it's not symmetrical. That's why it moved a little bit. I will play it again. So to see the result, I move to the result tab and I click play so I can see the animation. I will show you how you can see other results and extract other things that are more useful into your design. You can also go to Analyze and open Animation Play. This will give you more flexibility in playing the animation and moving to other time steps. Now let's give it some initial condition. To do that, I can go back to the modeling app. Right click on the arm, select move. Here notes that if I start moving parts, since I don't have enough constraints, like what you see here, it will move out of the pin. There are two ways to do that. First is to actually use the move, but move the handle before we move the part. So here, if I click on move handles only, I can put the handle on the top on the pin and then I start rotating. So to do that, I can go here and select the arc. By selecting this arc, now the handle is in the right place. I want to check the move handles and then here 30 degrees and click OK. Now we have an initial condition for the motion. Another option is to define the actual assembly constraint. This is helpful because every time you use the move, you have to select the handles, and if you have a big assembly, that's not very easy. So I go to assembly constraint. First, I will fix the pin. I click apply, and then I want to add a hinge. This is very similar to what we did in the motion. So I basically create a vector. Vectors should be aligned together. This means the center of the joint. Also the points should be in the center. So I go with between 2 points, between this point and this point for the first part, and for the second part I will use this face for the vector, and again I will go with 2 points. So the points are matching together, and then create the joint. Now you see that I have 3 constraints. One is keeping it in the center, which is not necessary anymore because the hinge is keeping everything in place, and the fix is fixing the pin. Now I can select and move the arm. You see the handle went to the default, but we don't care anymore, so I can move this without moving the handle to the right place. So 30 degrees, click OK, and I can save here and move back to the motion application. Here in the motion application, I don't need to change anything. I just run the solve and go to the result. Now we can see the result. Now, how can you extract these results to analyze them or to use them somewhere else? To see the results, you can use this XY result view. And based on the object that you are selecting on the motion navigator, it will show up different options. As we are adding different things to our simulation, you will see that options are different. So let's start with the displacement. For each option, you can see that there is absolute and relative, because in the joint, we have action and base. So we could read the action, absolute position, for example, or absolute force, or we could read the action position relative to the base. So here you can select if you want to read the absolute of displacement, velocities, force and acceleration, or the relative to the base. Here I go to displacement. You can read the displacement magnitude. This joint is not moving, so that's why it's a constant. And I move on to the rotations, then I go back to the Euler angles and explain them. Here you can see the coordinate here. So my rotation is along Z axis. If I select RZ and click on the figure that I have on the chart and click on the toolbar, I can move between the charts that I'm adding. So this is the displacement, or RZ, as expected. It is showing the absolute, so that's why I start with minus 180, and if I play, we can see the changes in RZ. I can see the RY is not changing and RX is not changing. This is the creep, that the initial movement that we have in this system. Otherwise, it's very small, so you can ignore it. So what are the Euler angles? These are actually pitch, yaw, and roll angles. So it's kind of relative motion. If you want to read the pitch, for example, this is the pitch angle. And it's all in degrees. You can move to relative, and I will show you the similar pattern, but different values. For example, this is our absolute rotation. And if I click here, now you see our relative motion. Because it's relative, it now starts around 0 and moves up to 60. So because it's relative, it will start at 0. We can also read the forces. The force magnitude, you see the force is changing, and the magnitude means the magnitude of all three components. And the Z, since there is no friction, there is no torque being transferred along the Z axis. So this is how you can extract the result. Later in our next lecture, I will explain how you can evaluate the function or manipulate the result or analyze it inside NX.